the problems we've worked up to this point are mathematical problems. The next part is a thinking problem. And it's relatively simple. The hard part is you got to make sure you keep your point of view. Okay, so what we're really going to do is assess delta H, delta S, and delta G for each type of problem. Okay, so we'll work through here. All right, when a bottle of perfume is open, odor-causing molecules mix with air and slowly diffuse through the entire room. Is delta G for this process positive, negative, or zero? Same thing with delta H and delta S. Now, it's usually easier to do delta H and delta S first because delta G usually follows. You can start with delta G, but it's easier to start with delta S and delta H. Now, here's the ugly part and the easy part. There are multiple answers for a lot of these, and I'll go through that with you on the next one. This one's pretty much a one-way thing. So let's just look at it. So if you think about it, perfume is you're going from a liquid into a gas. So energy is needed to vaporize all the liquid. Okay, if that's the case, we need energy. So enthalpy is positive because we're simply converting the perfume liquid to a gas. Now, on the other side, if you think about the disorder, there is more, much more, disorder when you go from the small bottle to the entire room. So remember, disorder has to do with the number of states and the possibilities. Think about it. If all of the molecules are contained in a little bottle, and then you open the bottle, and now they're all over the room, the disorder is tremendous. So that's positive. So in this case, we have delta H says don't go, and we have delta S says go. Which one wins? Well, in this case, delta G is going to be negative. Why? Because, and this may sound goofy, but this happens. If it is something that does happen, okay, spontaneously, it doesn't matter how cold the room is. If you pop the lid off the container, it's going to move all over the place. Then delta G has to be less than zero. Now, what you know is that if something vaporizes and goes around the room, it's going to do it much faster if the temperature is warmer. But it will still do it even if it's cold. Now, this is different from a non-spontaneous process like ice. Okay, ice forms spontaneously in the freezer because the temperature is really low, right? Does ice form on your counter? No. Okay, and that's because at that ice formation is temperature dependent. Okay, perfume moving throughout a room is not. If you put clothes out on the line when it's below 32 degrees, they're still going to dry. They'll freeze first, but you'll still move the water off of the clothes. So it's still a spontaneous process even at low temperatures. It just takes longer. And remember, spontaneity has nothing to do with time. Okay, so now that we've worked through this one, let's do another one. Okay, and this is one of my favorite ones. Humpty Dumpty sat on a wall. Humpty Dumpty had a great fall. All the king's horses and all the king's men couldn't put Humpty together again. All right, so, wait, what? Okay, now there's always the conspiracy theory that Humpty Dumpty was pushed. But the trick to this one is your frame of reference. Okay, so a lot of people want to talk about how Humpty Dumpty got on the wall. Okay, so if we talk about it that way, we'll have one set of answers. And let's go ahead and do this one, and then we'll go the other way. So Humpty Dumpty got up on the wall. Okay, so we have delta H, delta S, and delta G. Okay, so delta H has got to be positive because somebody did work to put him up there. Last time I checked, eggs, because he's an egg, don't just appear on walls. That is not spontaneous. So then we look at delta S, and we're talking about the order. And when we talk about it, it said that, you couldn't put Humpty together again. So Humpty Dumpty right now is whole. He is whole. There is much order. So delta S has to be negative because you got an egg and it's all together. Okay? So that means that if both of these say no, then this one has to be delta G has to be positive because this doesn't occur. Okay, so you're like, fine. Let's see what else we can do with this. Some of you are going to go with the fall. Or if you're the conspiracy theory, Humpty Dumpty was pushed. Okay, so when he goes to fall, okay, delta H is going to be negative. Why? Because no work was done when he fell. Okay? When he went over the edge. No problem. Okay? So then when he fell, delta S, he's in pieces. Yeah, everybody has dealt with an egg. So the eggshell is in multitudes of pieces. Well, last time I checked, that is definitely an increase in disorder because there's much disorder. So, therefore, delta G is going to be negative because it's spontaneous to fall off, not to fall on. So when we work this problem, we've got the issue of frame of reference. And this is kind of the trick in terms of how you do a frame of reference. Now, one of my favorite ones that I like to do, is, let me add in another page here and switch colors, because one of my favorite ones that I have done in the past is a sandcastle. And the important part is there's no right or wrong answer to this question as long as you maintain a frame of reference. Okay? So I did this one on a test a while back. And so I just set a sandcastle. So I had one group build it. Okay? So delta H will be positive because work was done to build it. No problem there. Delta S is going to be negative because you made the sand more orderly by taking it from everywhere, ordered, and you can say from many places to one. And delta G is obviously positive because both of these say no, so delta G has to be no, but you want to put it within the frame of reference. And so, sandcastles do not spontaneously appear. not spontaneously appear. All right, that was the main one. The next one that I had was when it comes down. All right, when it comes down, and you can do this, wave action, wind, whatever. Okay, so delta H is going to be positive. A little work is done. And actually, if you think of it as waves or wind, when it occurs, um, the work is done, but it's really given off by the wind and the waves because the energy is moving and then it'll hit the sand and make it disperse. Okay, so if you'll notice, I started with the positive, and then as I thought about it, no, it's actually given off. The energy is given off by the wind and the water as it hits the sand. Okay, delta S will definitely positive because the sand is from one spot to all over. So my disorder has occurred. Now, delta G, on the other hand, comes out equal to negative because this is spontaneous. It is spontaneous for sandcastles, dunes, whatever on the sand to be eliminated because it just naturally occurs because the energy is given off by the water and the waves, and it goes to more disorder when it moves around, etc. Okay, so these were the two main standard answers. And then, of course, I had one that was kind of the fun one. It's going to come down, but now you got a 4-year-old. Okay, he's going to kick it. Okay, so the delta H is going to be, and this one you can go either way. First off, the kid's going to have to do work in order to make it happen, but that is going to give off heat, which will increase S. That's a different story. And delta S is going to be positive because, again, you go from one spot to all over. And then delta G is where you can go either way on this. If you're dealing with a 4-year-old, this has to be spontaneous because 4-year-olds cannot stop. They're going to kick it down regardless. It may take energy, but they have a lot of energy to give up. So in this case, it's coming down, but it's by a 4-year-old. So the bottom line on this is, what's the right answer? Any one of these is the right answer. All three of them are not. So for example, you can't have a positive here and then move over here to a positive here. That doesn't, you choose your frame of reference. You decide whether you're building it, whether it's coming down by nature, or whether it's coming down by a 4-year-old. It doesn't matter what you pick. It's a matter of frame of reference. Okay? And if you're concerned with this, I'll give you a sample that you can do, and you can send it to me and I will correct it, and we'll do the standard a beehive. Everybody should know what a beehive is. If not, Google it. Okay, so do that, and you can email it to me. Please email it to me in D2L. I know I made a big deal about never watching D2L, but never thought I'd be making these lectures in my spare bedroom either. But so the D2L helps me keep up with y'all's stuff differently than all the other junk I'm getting from faculty, staff, spam, whatever. Okay, so this is your non-math question, and remember this one involves a frame of reference. Okay, so the next one goes back to math. We're going to go back and do a little bit more math here. These are the reactions, and if you'll notice, you're like, this is deja vu all over again. We just talked about these two. You can do the same thing. All the values are in Appendix 2. If you want to do these, knock yourself out, but again, they're going to be on mastering, but not on the test, okay? So what's free about free energy? Again, these don't go on the bonus points on the test, but they're still interesting to read. This one's actually kind of cool, so you might want to read over that. This chart, this table it works on spontaneity, positive, negative. I don't remember what's on top. I lost something in the translation, but we've already been through all of that. Okay, now the last one I told you was we did delta G is greater than 0, less than 0, and now we're going to do equal to 0. So when delta G is equal to 0, then we're at equilibrium. So what we can do is take our free energy expression, and notice this is non-standard. Okay, so we're not at our standard conditions. So if delta G is equal to 0 and the reaction is at equilibrium, and for that Q is equal to K, remember Q is greater than K is moving one direction, Q is less than K is moving another direction. If Q is equal to K, then it's at equilibrium. So we come up with this equation, and again, notice that R, we're dealing with the joules per mole K value, and we can rearrange it here, and remember the inverse of the natural log is E. So we can determine the equilibrium constant by raising the free energy times the R, which again is 8.314, times the temperature in Kelvin. And that will give us the K value. Now, this equation is on the formula sheet. And the formula sheet should be posted in the exam folder. I will make sure, the last half of it, I will make sure that it is in there. Do make sure you print it off before the test, because the lockdown browser will not let you play with it. So you definitely want to be able to look at it. So here we go. Now, we said that we could look at this graphically. If we look at a reaction, notice this point is the equilibrium point. If delta G is large and positive, K is reactant favored. If it's large and negative, it's product favored, which makes perfect sense, because if it's positive, it doesn't want to go forward. It's not spontaneous. If it's negative, it wants to go forward. If it's basically 1, then you are at equilibrium. So no, you will not be asked any graphs on the test, but when you get to organic, Dr. K, especially, I don't know about Dr. Buffon and whoever else you might have, like to get into graphs so you can say, oh yeah, I saw that at one point in time. Okay? So now we're going to work a problem, but before we do that, I want you to look at stuff. Notice that our K here is really small. Okay? That means our delta G is very large and positive. It's even larger and positive. Notice that our value is even smaller. If it's small and positive, then our K value is a small negative. If we are basically small and negative, we have a small positive. If we're large and negative, we have a large positive. So they're related. So the question always is how are they related? Okay. So we want the Ka for formic acid. We're told what delta G is. And remember, K is equal to E to the minus delta G over RT. Oh, yeah, that's what I did wrong. Okay. See, I'm looking at my math and I've already lost something. I want to double check something before I proceed. Yes. Don't forget this negative. I did that. And I'm going to make sure real quick. I'm going to take a second and make sure that it's on my constant sheet, because you know what, guys? I went to go work that one and I got a positive value. I mean, a wrong value. And I don't see it in that form. So I will add it in that form. I'll just write it on and repost it. So don't sweat the small stuff. Okay. So here's our value. Now, notice a couple things. Our temperature needs to be in Kelvin. So it's going to be 298.15. And the R value is 8.314 joules per mole K. And okay, that's what we need. So we're going to have E. Wait a minute. That's in the R constant is in joules. So we're going to have to put delta G in joules. So it's 21,300. Remember, we're moving it two places. Joules, per mole, divided by 8.314 joules per mole K times 298.15. So this gets a little crazy. So what I'm going to do is just solve for it. So I get e to the minus 8.5928. And as I said, when you look at your calculator, the inverse of the natural log that we used back in the kinetics is e. So I did it without putting the negative in. And I knew the number didn't look right. So I got 1.854 times 10 to the negative fourth. And don't remember what formic acid is, but this makes way more sense than the answer I got. So remember, if I had done this on the test, I'd have lost a point, maybe two, for dropping the negative. So don't do that. And I bet I did it on this one too, because I used the same equation. So again, K is equal to E to the minus delta G RT. All right, now I'm going to just come over here and do negative delta G over RT. So it's easier. This in Kelvin is 311.05 K. My delta G value is going to be negative 15400 joules per mole when you convert it. So we get negative on a negative 15400 joules per mole divided by 8.314 joules per mole K divided by 311.05 K. So I got a negative 5.95498, which means my value comes out to be positive 5.95498. So if I go back over here, I got e to the 5.95498, and again, I'm going to have to redo it because when I ran it the first time, I dropped that negative, so 5.95498, and that's goofy. I got I'm going to check that again because that just doesn't seem right. We got 15,400 divided by 8.314 divided by 311.05 times -1 times. I'm going to raise that. All right, I got K is equal to 385.67 joules. Okay. All right, that was not what I expected at all, but if I look at it, it's a negative and it's small. So we could rewrite this as 3.857 times 10 to the 2, so that would make sense when you do that. Okay, so again, make sure you carry the negative because, again, once I'm done with this, I will reach over here and write that in so that I have it. We'll be good to go. All right, now the last one is temperature dependent of equilibrium on constants. Remember, every time we talked about an equilibrium, there was a temperature associated, and you're like, well, what do we do with it? Nothing. Nothing, but you do have to worry about it because equilibriums are temperature dependent. So if you'll notice this, you've got the factor of temperature dependency associated with the energy term in this reaction with the natural log of K. And so while this is important, this is not something I'm going to worry about. So just know that equilibrium constants are temperature dependent. Okay. Driving non-spontaneous reactions, coupling reactions. This is actually a cool little lanyap that relates to biology, etc. And we are done with chapter 19. So it's 2 parts. A lot of the problems, and then the one problem that is going to be theory that'll be on there, and that's assigning delta S, delta H, and delta G on the test. Okay, and I will list the problems that will show up. All right, so we're done with 19.